All right, alkylation of the alpha position. Not only can we put a bromine on that position, I want to jump forward a little bit to section 5. I think this goes very well with our current understanding of enolates and enol intermediates and using bases to form the enol. So I want to jump forward a little bit. So jump forward to section 5, alkylation of the alpha position. The alpha position, we'll just label 1 right here, can be alkylated. It can have a new carbon group being added when an enolate is treated with an alkyl halide. That second step right here is just an SN2 reaction. So we can use a base to form an enolate, and then we can do an SN2 reaction with an alkyl halide. Super great second follow-up step, all right? Now, backside attack, kick out the leaving group. Be very, very careful with those R groups. Typical restrictions of the SN2. Remember, primaries and methyl alkyl halides are amazing at SN2 reactions. Once you get to secondary or tertiary alkyl halides reacting with a strong base and strong nucleophile, E2 elimination reactions dominate. So when we're thinking about what to bring up in our second step here, we're going to stick with methyl halides or primary halides. Okay? Beautiful. We'll talk about the aldol reaction later. The aldol reaction is going to be a competitor with alkylation. So we do use strong bases when looking at aldehydes and ketones. Regioselectivity is an issue with unsymmetrical ketones. And so that's what we're going to talk about first, not the aldol competition yet. We're first going to talk about regioselectivity. What happens if we have this starting material? Here's our starting material, and we want to alkylate. Well, I have 2 different alpha positions, alpha 1 and alpha 2. Which one do I choose? Well, it's going to be based off of the base. It's all about that base. So when we're looking at these 2 ideas, one side, the alpha 1 that I wrote there, is kinetically favorable. It's less stable, but it forms faster. Why? Less steric hindrance, okay? So if you're looking at these 2 sides, one will have less steric hindrance, and that's what we will call the kinetic enolate. The other side, what I labeled as alpha 2, is more substituted and therefore more stable, but it does form slower. It's what we call the thermodynamic enolate. We've used these terms kinetic and thermodynamic before. Thermodynamic always hinted towards a stable product, a more stable type ending point. Kinetic always went to forming faster. Okay, so here we have a kinetic option and a thermodynamic option. Again, looking at their pathways, kinetics, lower activation energy. It's faster to go to the alpha that has less things on it, more hydrogens, less other bulk, right? But it's overall more stable. Oops, 2 words, Lauren. More stable to form an enolate that is more substituted. It's just slower. Notice how high that activation energy is. Higher the activation energy, slower the reaction. Okay, kinetic enolate is always favored by irreversible conditions, LDA at low temperatures. Thermodynamic enolates are favored by reversible conditions. This could be using NaH at room temperature. You can also use alkoxides at room temperature, but in real life, you probably wouldn't use those. Typically, one of these two will be our setups. LDA at negative 78 degrees Celsius, super cold, not allowing enough thermal energy to reach the higher activation energy of the more stable enolate. NaH with 25 degrees Celsius, much more thermal energy is provided, and so that ends up putting the R group on the more substituted thermodynamic. So here's kinetic and thermodynamic. A malonic ester synthesis is a specific step of alkylation reactions when you start with diethylmalonate, and it's a great way to convert to a carboxylic acid. So the malonic ester synthesis takes diethylmalonate, this beautiful molecule right here, and at the end of the day, it likes to add on carbon groups and to make carboxylic acids. So first thing that we use is a base. Here we get to use an alkoxide simply because the pKa of diethylmalonate is very, very low, 13 pKa, and that's because of resonance stabilized. So again, that enolate can then do an SN2 reaction. All of the SN2 conditions apply, right? And then in a third step, we use H3O plus to hydrolyze. This is a chapter 20 reaction where we are changing the ester groups to carboxylic acids. If we decided to use heat, one of the resulting carboxylic acids can then be decarboxylated. And it is involving an intramolecular style reaction where we are driving off carbon dioxide. So notice here in the very bottom, we've rearranged our dicarboxylic acid in order to see that six-membered ring formation again. Let's look at this reaction where we are actually going to be driving off carbon dioxide. The pi bond will pick up a proton, causing this oxygen-hydrogen bond to relax down. This forms carbon dioxide. There's the CO2 forming, and it kicks off that last bond to the alpha carbon to make a double bond. Okay, so here's our alpha. The resulting enol will tautomerize to the keto or the carboxylic acid form. All right. Now, what does this look like overall? We have first step as a base to form the enol or enolate. Second step, we throw in a secondary or a primary or a methyl alkyl halide. This is our SN2 step. And then third step is H3O plus and heat. We decarboxylate, drive off carbon dioxide. The decarboxylation mechanism you do not need to know. You would need to know the first two steps of the malonic ester synthesis, and then the decarboxylation step. I would just want you to be able to erase one carboxylic acid, and that's the end of it. Notice there are two protons on the alpha position, so there is up to 2 different R groups that you could have on this synthesis. The acetoacetic ester synthesis is the exact same thing. The only difference is we are using a beta keto ester One side is an ester, one side is a ketone. So at the end of the day, when we decarboxylate, we make ketones instead of carboxylic acids. Same exact reaction.